Let's discuss a question from Rankine cycle, and then basically what is asked to find out the efficiency of Rankine cycle. So let's draw the Rankine cycle in a HS diagram and a TS diagram, sorry. So you have that dome shape that you can see it here, and once the steam is out, so these are the constant pressure processes. Okay, so let me draw a constant pressure process for 4 MPa, and this is basically 15 MPa, 15 kPa, sorry. And the starting state, that is the inlet to the turbine, is somewhere here, that is at 4 MPa, 370 degrees Celsius. It's somewhere here. It's a superheated condition, otherwise both HF and HG would have been given. Only H is given, that means it's a superheated condition. So this is our point number 1. Then the point number 2, when the turbine expansion in turbine takes place and the turbine produces some work, the final state is number 2. Now we need to find out whether it's outside the dome or inside the dome at 15 kPa. Now one thing is sure, that the entropy remains constant. So the entropy is 6.5821, and the final also entropy remains constant. Now if you look at this SG at 15 kPa is 8, which is greater than 6. Now 6 should be the entropy at state number 2, so it is just below, just before the dome, right? It's in a superheated, so 1 is superheated, 2 is saturated, not saturated, it's a mixed state. Superheated, it's saturated, not exactly at point to saturated, mixed state. It's a wet steam, right? That you can say. And then you have the condenser where it rejects heat, and then you have the pump. So pump is also an isentropic process of state, and then the boiler. Okay, 3 4 is a vertical line. Okay, so now we need to find out the efficiency. The efficiency is net work done by Q, the heat addition in the boiler, which is 1 to 4. Okay, so let's first find out that. So point number 1, H1 we know. Okay, so remember that. Now first we need to find out state 2, because it's a wet state. So what is, so entropy at 1 is equal to entropy at 2. Entropy can be represented as S2F plus X into S2G minus S2F. So the dryness fraction, so the entropy has to be constant, so isentropic process, right? So S1 is 6.5821, and SF are, these are the entropy. So we need, first the idea is to find out the dryness fraction at 2, so that we can get the enthalpy at 2. So 0.7549 plus X into 8.0085 minus 0.7549. So once you this is just simple equation from where you can get X, and X comes out to be 0.8. So the dryness fraction is 0.8 at this point. So let's now see what is the enthalpy. So the enthalpy at H2 is HF plus X into Hg minus HF. So the value of HF is basically, let's see the value from the top. Okay, so HF value is basically 225.94, and dryness fraction we got 0.8, and Hg is 2599.1 minus 225.94. So with the help of this dryness fraction you can get the so-called enthalpy, and that enthalpy value comes out to be 21 24 0.46 kilojoules per kg. So everything is in kilojoules per kg. So once we got H2, that's okay. Now the thing is that turbine work is H2 minus H1. The isentropic work is H2 minus H1, but it's there is an efficiency. So the actual turbine work will be some efficiency into the isentropic work. The isentropic work is basically when it's a straight line. So that is straight line is basically H1 minus H2, right? That is because it's a open stream processor, so the difference in the enthalpy is the work done by the turbine. So 0.9 into H1 is basically there is 3092, that is the superheated steam enthalpy at 4 MPa starting point, minus 2124.46, the one which we got it right now. So this value is substituted here. So what we get is, after multiplying with 0.9, is 871.2 kilojoules per kg. So this is the net turbine work. Now the pump work, how do you get the pump work? The pump work can be easily we get is from the integral VdPa, that is the specific volume there into the pressure increase. Okay, this is how we get the isentropic pump work. Okay, so and that is in fact the increase in enthalpy, okay, from H4 to H3. So now the specific volume is given as there, that's why the specific volume is given as 0.00. So we utilize the liquid part of that, 1014 into the pressure is 4 MPa, so let's convert in kPa, so that is 4000 kPa minus 15. Okay, so this comes out to be, if I in kPa, so kilojoules per kg, and this comes out to be 0.04. So it's very negligible compared to the turbine work. In fact, even if you forget to calculate, that's okay, because so this value is basically H4 minus H3. Okay, so H4 minus H3 is 0.04. So let's calculate H4. H4 is H3 plus 0.04, and H3 is basically the value from the table. H3 is basically okay, H4 is H3, let me write like this, 0.04, and H3 is nothing but HF at 15 kPa, at 15 kPa HF. Beg your pardon, there's some problem with this. Okay, so this HF at 15 is 225.94. so 22.94 plus, okay, 225.94 minus 0.04, and that is nothing but 225.9, right? So this is the value of H4. So now the heat addition is basically, let me do it in a next page. Okay, so now the Q addition, okay, the Q addition will be the heat in the boiler, that is from 4 to 1, will be H1 minus H4, and H4 we already got in the previous, just some time back. So H1 is, so when you subtract this, whatever we got, H1 is 3092.5, and H is 22, H4 we already got 224.9. so this value comes out to be 2862.5. okay, 2862.5 kilojoules per kg. Okay, so now the efficiency is the net work done, that is work done minus work required for pump by the heat that the boiler adds. So work done by the turbine, which is work done actual is 871.2. Pump is again very small, 0.04 by this value 2862.5, which we just calculated. So this ratio comes out to be about 30 percentage, 0.03, 30 percentage roughly. So this is the answer, 30.30. Thank you. So only thing is, you need to know if you are able, if you are confident about the cycle drawing, if you are able to draw the cycle in a TS diagram, and if you know how to calculate the enthalpies at various points, then it's just basic thermodynamics. Thank you.